Okay, in this last video of the chapter, we're going to talk about the spectroscopy of carboxylic acids and their derivatives. So a lot of this information is going to be review from when we covered spectroscopy last semester, but there are a couple of specific details that are relevant to these types of compounds. So carboxylic acids themselves are one of the easiest compounds to identify in IR spectroscopy. They have two very intense signals. One of them is very unique to carboxylic acids. So the first one that all carbonyl compounds have is they tend to have an intense CO stretching vibration in the range of 1700 to 1800 wave numbers. And oftentimes people describe this as a sword. And we saw this same type of peak with the aldehydes and the ketones. What makes the carboxylic acids unique is the peak that we get from the OH stretching of the carboxylic acid itself. And that tends to be an extremely broad peak between about 2300 and 3400 wave numbers. And oftentimes you'll see this described as a hairy beard, right? Because we have a really broad signal, and then we have the peaks from the CH stretches in other places in the molecule that give it this sort of hairiness at the bottom of the beard here. But anytime you see this really broad peak between 2300 and 3400 wave numbers, this is a dead giveaway that you have a carboxylic acid. So that really broad peak only shows up in carboxylic acids specifically. But all of the carboxylic acid derivatives that we've seen in this chapter will have that carbonyl stretch. Now what's interesting is the different carboxylic acid derivatives tend to have that stretch appear at slightly different frequencies. And in general, where that frequency appears correlates to the reactivity of the groups. So the acid halides were the most reactive, and its peak has the largest frequency. And the amides are the least reactive, and coincidentally, they have the weakest carbonyl signal, or the lowest frequency carbonyl signal. And so this can sometimes be used to identify the different, or the type of compound it is based on exactly where this stretch appears. Now that being said, it can sometimes be a little bit difficult, right? If you're wondering, okay, do I have an ester or do I have a ketone, right? Well, sometimes it's very hard to tell, especially depending on the resolution of the spectrometer. Is that peak at 1740 or is it really at 1720? So sometimes it's easier than other times, right? Distinguishing an amide from an acid halide is pretty easy. We should be able to tell the difference between, 140 wave numbers difference in where a signal shows up. But if it's between two things that are relatively close together, the resolution of the spectrometer may not be enough to tell us that. But this peak does shift based on the nature of the functional group. Another thing to remember with this carbonyl signal is that when it's conjugated, it tends to show up at a lower frequency. So as an example, if I had this ketone, we would probably expect it to show up somewhere around 1720 wave numbers. If I had this ketone, because I can draw the resonance structures because I can draw these additional resonance structures, this gives this CO bond more single bond character. That's going to shift at the lower frequencies. We would expect this ketone to show up around 1720 wave numbers, whereas this ketone we'd expect to show up somewhere around 1680 wave numbers. The other peaks that we might expect to see in our carboxylic acid derivatives, nitriles appear in the triple bond region. They generally show up around 2200 wave numbers. Sometimes the peak is intense, sometimes it's not very intense. Amides should also show their characteristic signals from the amine part of the amides. If I have a primary amine, that's the part of the amide, then we expect to see two signals because we get both the symmetric and the asymmetric stretches. And in the case of a secondary amine that's part of the amide, we would expect just one signal because we only have effectively the symmetric stretch. Finally, when we consider NMR spectroscopy, most of these derivatives don't have hydrogens that are specifically part of the functional group, so they don't really show up. I think the one exception are the carboxylic acids, and much like the aldehydes, these are shifted really far downfield. So the hydrogen that's specifically part of the carboxylic acid generally appears as a singlet because there's no other neighboring hydrogens, and it's down around 12 ppm. All of these groups are going to have the carbonyl carbon, and that tends to appear around 160 to 185 ppm, and that's just about the only thing that's shifted that far downfield. We haven't talked about carbon-nitrogen triple bonds, but it turns out they appear between 115 and 130 ppm, and that's not actually in our table, so we could actually add it. The C triple bond N would appear in that box, and so our nitriles, we would expect to see the carbon from those in that region.